Hey learners, and welcome back to the video tutorial where we were looking at two masses being pulled or being released from rest on a pulley, a cylindrical pulley with a frictionless surface. We've set up our free body diagrams, and now we're going to try and connect all of these things together to solve for our acceleration. Once we know our acceleration, then we can go back and we can solve for a particular force. We can solve for final velocity after we cross, this certain height right here. Anything that we want to solve for, we can once we have our acceleration. So we've got our free body diagrams here. How do we connect these things? So we start with Newton's law for each mass. So I've got summation of my forces equals m2 times our acceleration. And then for our wheel, I've got the summation of my torques, and that's going to equal I times alpha. And we said that to connect alpha with our translational acceleration, it was equal to A over R. So we're going to come back to that here in just a minute. So let's start with M1. Summing up my forces, it's easy for M1 because normal force and weight are going to cancel out, and so that leaves us with just Ft1 being equal to M1 times our acceleration. Now, I've established that M1 is moving to the right, and I've given that a positive acceleration because I've just left A as just A. So I'm going to carry that over for M2, and I'm going to say M2 is moving down, but I'm going to say down is positive. So summing my forces for M2, I've got Fg2 minus Ft2, and that's going to equal M2 times our acceleration. So if you look at this, solving for our acceleration in terms of things that we were given, I don't know what Ft1 is. I can make one substitution here for M2, and I can say Fg2 is that weight, M2 times G, minus Ft2 equals M2 times our acceleration. But we still have this as an unknown, and then this is an unknown. If we're trying to get acceleration in terms of G, M1, M2, and the mass of our wheel, M. So I have 1, 2, and then 3 unknowns, but I just have 2 equations. But as we saw before, I've got a whole other object that I can look at, and that's our wheel. Now, our torques, if I go back to our wheel here, our 2 torques that we've got going on. Ft2, if you want to do the right-hand rule, Ft2 is giving us a torque that is into the board, while Ft1 is giving us a torque that is out of the board, or page, or screen, or however you're viewing them. It'd be weird if you were on paper, but... So, there's 2 torques fighting against each other, but Ft2 is the one that's going to win out. So, I'm going to make that so with our... not force diagram, but with our kind of torque summation here. So summing our torques here, the torque from Ft2 minus the torque from Ft1, torque, not force, equals I, which is 1/2 mr squared times alpha. Now, I can, for each of those torques, plug in what that torque actually is. It would be Ft2R minus Ft1R, and that's going to equal 1/2 mr squared times our angular acceleration. But I'm going to make one last substitution, and I'm going to say that's A over R. So I've got 3 equations now. Here's 1, 2, 3. And I've got 3 unknowns. I've got Ft1, I've got ft2, and then I've got acceleration. And those same unknowns are over here. There's ft2, there's ft1, and there's acceleration. So now that we've got our three equations, we've got our three unknowns, now we can go ahead and start making our substitutions. And if you look, ft1 is already it's already isolated over here. I've got ft1 equals m1a. So I'm going to take this m1a and I'm going to plug it in for where there is an ft1, which is over here. Now, I can go ahead and also solve for ft2 right here. If I add ft2 to the other side, whilst subtracting, to the other side, I can end up with something that looks like this. I'm going to get ft2 equals m2g minus m2a. So that is my next substitution that I can pop in right there. And so if I do that, I'm going to end up with only one equation and our only unknown being our acceleration. So let's go ahead and make those substitutions right now. For ft2 right here, it was m2g minus m2a, all of that times r, minus ft1, which was m1a, and then times r, and then that equals that right there. So now you can isolate your acceleration so that you end up with only one unknown. Now, what I'm going to do is I'm going to divide this whole side by r, and I'm going to divide over here by r. If you look at that, one of these r's already cancels, and then dividing by r again, my r's cancel all around. So I end up with, I'm going to bring it down here, m2g minus m2a minus m1a equals 1/2 big M, the mass of our wheel, times a. Now I can't just divide everything by a because our m2g over here doesn't have an a. So when I'm isolating a, I'm going to get everything with an acceleration over to the other side. So adding all of those things over here, you end up with just m2g all by its lonesome over here equals, here we go, 1/2 ma plus m2a plus m1a. All of those have an a, so now I can factor that out. And now divide over that to the other side. You end up with an acceleration being equal to, so I've got m2 divided by 1/2 the mass of our wheel plus m2 plus m1, and then all of that times g. So kind of as expected, you end up with some fraction of gravity is your acceleration when you've got this system set up. Now, this method, looking at it, like taking a step back, this is fairly algebra heavy. The key thing that you need to be able to do is set up these three free body diagrams and then setting up these three equations. Once you can do that, then the math will just come with practice, but it will follow this similar pattern of setting up a system of equations for your system of objects and then solving. What we'll look at next is an alternative method to solving, not using our Newton's law route, but using our conservation of energy route.